All right. Mic check. Mm-hmm. Good afternoon. Right. Interesting. So for everyone's joining in, I'm just waiting a few more minutes. I'm gonna wait till 1:30 before I start. And okay. Remove. Interesting. All right, just another minute or two, and then I'll get started, everyone. Yeah, Jude, I think we're all a little tired. Alrighty, so I think that's enough twiddling our thumbs and waiting. Let's jump into our lecture today. Oh, let's go ahead. Is there a link on Blackboard or something? Okay, so Rivers, I thought I sent a Blackboard announcement. Let's see here. So, if anyone else is in the chat, can you just confirm if you got an email? Yeah. Oh. Okay. Yeah, I try and I'll always use this YouTube link to stream the lecture, so you can always just subscribe there and get it. But I also try and make sure that I send out an email. Alrighty. Okay, so it sounds like the Blackboard announcement didn't send out the email. Let me just, let's see here. Let's do. So at risk of flooding you guys with another million emails. Let's see here. Let's edit this. And just send that email out again. Yep. Alrighty. So, hello everyone. Let's get ready to dive into our next section on the interstellar medium. And we're going to see lots of gorgeous pictures. Talking about the gas and dust in the cosmos is where we start to see a lot of the prettier pictures that people associate with astronomy. All right. So, the quick outline how today's lecture is going to go is that we're going to start talking about the space between the stars, talking about where is the gas, what is out there, and some of its properties. And then we'll go in a little detail about, we'll distinguish between the dust versus the gas. And the shortcut, we might try and think of dust and gas as the same thing, but as scientists, we'll distinguish them in a bit more detail. And at the very end, we'll start getting our way back into the stars. We've talked about how our sun's this nuclear powerhouse. We, in section 7, mentioned how the protostar forms from the nebulas. Well, here's some pictures of nebula. So we'll go over again how the nebulas collapse down and eventually form the stars. So, for starters, let's just do a quick reading quiz. All right, and we're going to say, all right, astronomers, we're going to use this term interstellar matter, and what exactly are we referring to? Are we talking about just the planets around the stars? Is it a bit more than that? Is it the comets, asteroids, and meteors? Remember when we talked about our solar system, you can talk about, say, like the Kuiper Belt. It's just that region of debris that's around the sun. Is it just the gas and dust between the stars? Or is it a bit more abstract? Is it the radiation, the light, the radio waves that are filling the void between the stars? Or throw away a fortune teller. Obviously, it's not going to be E. So, everyone's on top of this. Yes, when I say matter, we're talking about just the gas and dust between the space of stars, right? We like to shortcut and we like to say space is a empty void, but even in the coldest, darkest regions of space, we're still gonna find stuff. So, all right, let's start talking about what is in that stuff. This is a picture. Great example. We're seeing all sorts of different hotbeds of protostars forming and glowing. The dark clouds here, these bands of darkness, that's what we might call molecular clouds. Just these thick in astronomical sense, thick layer of just debris out there. And it's literally blocking the starlight from behind it. So let's start getting a picture of where we're at, what we're looking at. And here, you might be able to recognize that this is the Milky Way, just the Milky Way galaxy. But instead of being in the visible spectrum, we're watching it in X-rays. So we scan across everything we can see in X-rays, and we just see that we are flooded by X-ray light. And so what we realize is that our star, our solar system, is in what we call a local bubble. And in that local bubble, there is a lot of these high temperature particles. Specifically, we'll say that the density is very low. So the number of atoms present, and I'll have some figures to try and clarify that a bit. But basically, the number of atoms present is very low density. But these are very high temperature gases. Remember when we talked about the outer atmospheric layers of the sun? You had the corona layer, which was low density, high temperature gas. Very similar. In terms of density, we can say what the average density is. We'd say there's about 0.01 atoms every cubic centimeter. So take a small little cube centimeter, and there's only a tenth of an atom being in there. Not a huge chance. But those atoms are whipping around very rapidly, right? Remember, temperature is in essence a measure of their average speed. And so, sure, there's not a lot of these things, but they are really, really hot. And that temperature of about 1,000,000 Kelvin is why they're glowing in X-rays. So, some other terms that we can bring into this, and we can talk about what we call the interstellar clouds that exist around this local bubble. So this is the local bubble that our sun's about here right now is in. And we've entered a slightly denser region in the last 10,000 years that we creatively called, I'm not even making this up, guys, we call this the local fluff. The density material is just a little bit thicker, whereas around here, it's closer to 0.01 atoms every cubic centimeter. And here, we're dealing with something about 0.3 atoms every cubic centimeter. And the temperature has gone down. This gas is much slower. This fluff is moving at much cooler rates, closer to 7,000 Kelvin. So I keep talking about these cubic centimeters and this density, and I want to use these next few slides to try and give you a little bit of a visual idea of what do we mean. So let's start out density, the number of atoms in a given volume. So let's start. Let's say I have a cubic centimeter of air, a little bit smaller, about a fraction of an egg, basically, right? So take a tiny little bit of air, and in that tiny section, there'll be upwards of 10 to the 19th molecules zipping around and bouncing. So here, take 1 cubic centimeter, and I've got trillions upon trillions of molecules or atoms bouncing around. Well, let's apply a vacuum, right? I'll hook up a vacuum, suck the material out, start trying to pull all the atoms out. And we define a vacuum to be when there's no gas present. Well, even the best vacuums on Earth, they only get down to about 10 to the 10th, about 10 billion molecules per cubic centimeter. So I can still take my little cubic centimeter box, and even though I've put the best, strongest vacuums that humanity's been able to create, we still got about 10 billion particles just flying around, floating there. So now we go into the vacuums of space. All right, we go into that interstellar medium, and there we'll say, look, out in that medium, there's an average density of sometimes around 0.1 atoms every cubic centimeter. Or put that in perspective, here's our cubic centimeter boxes before. There's one atom in a 10 cubic centimeter box. You're getting closer to about the volume of a little egg. So take an egg and go into the deep vacuum of space. That egg will have one atom in it. And that's the density that we're trying to deal with. So like I said, space is very big, and it's mostly empty, but a crucial part is that it's not completely empty. Even in the darkest, coldest, loneliest places, you're still going to find some number of atoms just floating around there. And this is where things get complicated. Right? That matter, it's not distributed homogeneously. Think of it this way. It's not like there's just this big pool of water stretched out thin across the cosmos. You're going to have regions where it's very, very densely thick. Nebulas are the perfect example of that. You'll have regions that are even super thick, like us here on Earth. We're a very dense pocket of atoms together. And then you'll have other spaces that are closer to almost no atoms there. So, wonderful question to try and contemplate how much stuff out there is to do a rough estimate of the amount of matter out there. We're going to say how much mass is in, say, our galaxy. And so here's the point. How much gas is there? We know the density is very low for most of space, but we also know space is very large. So let's try and put some numbers to this and figure out basically how much matter, how much gas is out there, and how much of it can be used to do stuff. So we're going to do just a straightforward approximation. And by straightforward, I mean we're going to use the next few slides to grind this out together. But it is a simple setup. I say, how much mass is the gas in our Milky Way galaxy? Well, how big is the Milky Way? Figure out the volume. Say, how many atoms per a volume exists? We've already been talking about saying there's 0.01 or 0.1 atoms per cubic centimeter. So you say, what's the density of atoms in our galaxy? And say, what's the mass of an atom in our galaxy? So we'll start with the hardest one. We're going to do the volume first. So here is our picture. Remember, this is an approximation. Still good if we expect to be within an order of magnitude of the correct value. So in our trick, we're going to take the Milky Way galaxy and we're going to treat it like a perfect cylinder. We're going to say it's a cylinder that is 100,000 light years across, and it's got a thickness of about 300 light years. Right? So if we treat this as our cylinder, there's our radius, and here's our height of the cylinder. So we can say the volume of the cylinder is just pi r squared, the surface area of this disk, times the height, or the 300 light years. So go ahead and do that calculation. We're going to have to be toying with units here. So I'm going to go through these a little bit by a little bit. So once again, we're doing this, the volume circle, or cylinder, pi r squared h. Our radius was the length, the radius of the galaxy. So the radius of our galaxy is going to be 50,000 light years. Let's use my highlighter. Right. We're going to have a radius of 50,000 light years. As a reminder, here's our spiral galaxy. Boom. There's that radius. All right. Now, the next term here, what's this guy? That's to convert, right? We're in light years. We need to be in centimeters to make all of our units consistent. So all we're doing here is converting 50,000 light years into centimeters. And straightforward, we just say, look, there's 9.5 times 10 to the 17th. There's 9.5, 10 to the 17th centimeters in 1 light year. So let's clear that out a little bit. So we're saying here is our radius squared of the gas in the in the galaxy. So table this number off to the side for now. It will come back for us when we actually do the full calculation. And let's get the density. Our density. We've talked about values of like 0.01 per cubic centimeter to much denser regions like 0.3. And so what we're going to do is just make an approximation and say, take a cubic centimeter and put 1 atom in there. And this we're going to approximate across the entire stretch of the galaxy. Say that there's 1 atom every cubic centimeter. Right? And this is basically a balancing act between the regions of very, very low density to regions of thicker densities of like nebulas or even potential stars. Now, we gotta get the mass of an atom. So, quick question for you guys. Most of the material in the interstellar medium, what is it? What is most of the stuff that's just floating out there? And I'll hold here for a second, see if you guys comment in there. All right. All right. So, everyone's being quiet, but I'll just continue anyways. So we see regions like these, nebulas, tons of gas, and we might be led to think that there's a lot of dust grains out there, which sure, there's plenty. But our universe is mostly hydrogen. In fact, if you try to count up all the different types of atoms out there, is there another? Okay, let's stop the recording. We lost the last 30 seconds. Okay, we did not hear that. Okay. All right, coming back. Is the stream going again? All right. And we're back. Okay, so let me go back to the question. So we're saying most material, what is most material in the interstellar medium? And we see pictures like the nebula all the time. We see these nebula, and you might think that these are going to be things like dust grains, because you see a lot of these different, bright, beautiful pictures. Hold on, okay, let's pause again. Sounds, we're not hearing audio anymore? All right. It says I'm streaming. All right, let's pop this out. All right. So quick check, are we back? Is the stream alive again? We lost me at slide 10. Okay. Oh, that was a bad place to get lost. I'm sorry, guys. Okay. Alright, so I'll just do this back from the beginning of it. So let's... Alright, so we said that we're treating the Milky Way as a cylinder. Alright, so as a reminder, here's the cylinder that we're treating it as, and we're going to use, if the diameter of the Milky Way is 100,000 light years, then we're going to use for the radius 50,000 light years. All right. So, treat it as a cylinder. We're going to say, hey, the radius is 50,000 light years. We need to be worried about units, right? We're in terms of light years. We're going to have later terms are in cubic centimeters. So we want to convert our light year, our distance from light year to centimeters. And that's the point of this term here, this 9.5 10 to the 17th centimeters. That's to convert from light years to centimeters. And it's the same term here, 9.5 10 to the 17th. Right? That is how many centimeters there are in 1 light year. Right? So, do the conversion, right? You've got your radius here, square it up, do the height, that 300 light years, the thickness of the Milky Way galaxy, and we'll get to the volume of the Milky Way galaxy, about 10 to the 66 cubic centimeters. So now, table this equation, table this volume, and we'll use it when we finish filling in everything else. So we'll bring this number back at the end. Let's establish what we mean by the interstellar density. What we're saying is the number of atoms per volume. So as continuing on our approximation, we're going to say we're going to take 1 cubic centimeter of space and approximate that 1 atom is there. Now, let's see, this is an approximation. We said in the deepest voids of space, it's somewhere upwards of 0.1. And if you go into like the thicker nebulas, it's going to be a higher density. So we're trying to average everything out. And that's why we're coming up with saying 1 atom per cubic centimeter. Next thing to figure out is going to be atomic mass, the mass of an atom. So what we're going to do there is say how much material is out there. What type of material is most of the universe? And you're going to see pictures like these nebulas, and a lot of people might jump to conclude that there's a lot of dust grains in the universe. They're going to say there's a lot of just dust, debris, but it turns out that most of this is going to be hydrogen gas. A whole spectacle of different colors coming from the cosmos, and most of it's still just going to be hydrogen. If we counted up the atoms in the universe, you'd find that hydrogen is about 75% of the universe. So, with that said, we're going to say that just every atom across this galaxy is hydrogen, and hydrogen has a mass. The mass of just the proton is going to be 1.7 10 to the minus 27th kilograms. So we're going to take all of these values, take in the volume, that 1 atom per cubic centimeter, and the mass of an atom to get the mass of the galaxy. Technically just the luminous mass, but We'll touch on that again later in the semester. So let's plug everything in, right? The volume we found before, 10 to the 66 cubic centimeters. We say, on average, we're estimating there's about one atom every cubic centimeter of volume. And that atom weighs 1.7 10 to the 27th kilograms. So stitching all of this together, we're going to find there is about 10 to the 39th kilograms of just stuff out there. So now we're doing this game, like I said, way back at the beginning of, well, this is a really, really big number. What does it mean? So let's rescale this. Instead of talking about 10 to 39 kilograms, let's compare it to something that has a bit more meaning to us. Let's look at the mass of the sun. Remember, circle dot means sol. So the mass of the sun is about 2 times 10 to the 30th kilograms. And let's just compare. The mass of the galaxy, the total mass of the galaxy, divided by the mass of the sun, right? 3.5, 10 to the 39th, divided by solar mass, 2 times 10 to the 30th. We're going to find that the mass of the galaxy is 1.75, 10 to the 9th times bigger than our sun. So what that means is that in the galaxy, even though it is mostly empty space, there's still enough stuff out there to make about 2 billion more suns. And just our sun, just a average medium sun, there is enough matter in the huge void of our galaxy for 2 billion more of these stars. That is how big space is. That even though it can be mostly an empty void, there is still so much space that there can be room for so much matter. So one last definition to bring in here. We can say the interstellar medium. And it's just a callback from the very beginning of this bit. Right? We're saying all material between the stars. Right? We can find gas, and that gas can be found as single atoms. Sometimes they'll be ionized. They'll be stripped of electrons. So they'll be charged particles flying through space. Or we can find them in molecular form, where they're making atomic bonds and making these bigger molecules. And we'll find dust, cosmic rays, all this stuff scattered throughout the interstellar medium, the space between stars. Right? Most of the stuff is going to be concentrated in nebulas. In fact, 99% of this stuff is going to be hydrogen or helium. Right? And the remainder, that last 1%, that's going to be that interstellar dust. Right? The dust is going to be the slightly thicker, slightly bigger materials. These are going to be rocks, silicates. And here's an example of a dust particle. And for scale, this is a micrometer, 10 to the minus 6 meters. So coming into our next part, let's talk a little bit more about the dust. And one example of how we know about the dust being out there is you see these different bands of light coming off the Milky Way. And that's due to what we call zodiacal dust. So that's dust closer to Earth's atmosphere, scattering the light. So here's another diagram representation of the dust out there, right? And this stuff will range in sizes of, say, a couple molecules. So you're saying a few atoms stuck together, or a little bit bigger, yeah, upwards to 300 nanometers. So you're going to have a handful of atoms to a couple 100,000 atoms making a little bit of molecule. And most of the stuff is going to be some kind of rock. Could be silicate, could be graphite, just some kind of rock. And around that is going to be a little mantle. Definitely some sort of ice. It could be some type of water or methane or ammonia, something that is just frozen around that rocky core. So that's going to be our dust and the cosmos. Now, this dust is going to interact with light in a couple of ways. And so the first one, I want to use a rocking boat analogy. So in this analogy, you've got your boat and the waves, right? The waves are about the same size as the boat. Specifically, the wavelength is about the same size as the boat. So if the wave is the same size as the boat, what happens to the boat? It has a very rocky adventure, right? The boat will rock a lot because of these huge waves causing it to dip up and down. So if the wavelength is on the order about the size of the boat interacts a lot. So if I take my dust particle, if the wavelength of light is about the same size of the dust particle, then the dust will interact with that light. It'll vibrate a lot. Now, if I go for a long wavelength, then the boat has a simple ride. It's not a hard trip. And therefore, the molecule, the dust particle, if the wavelength is long, much longer than the size of the molecule, then it doesn't interact as much. And so the dust, right, what types of wavelengths of light can get through the dust depends on how big the dust is and the wavelength of light coming through. So definitely have this idea of the rocking boat analogy. The size of the dust, what light it blocks, is related to, or the wavelength of light that dust blocks is related to the size of that dust. So other things that can happen. You could have your interstellar dust particle, and you could have starlight traveling through the cosmos, right? And that dust is going to absorb some of it. And what happens? If I absorb some photons, say I go to the beach and try and get a nice little suntan, I'm absorbing photons, I warm up. If I'm hotter, if I'm a warmer object, then I need to give more thermal radiation to reach that equilibrium, right? I'm absorbing a bunch of energy, I must radiate it away at an equal rate. And so this dust is absorbing a bunch of photons and then starting to glow in the infrared spectrum. We're going to see examples of the consequence of this phenomena on our view of the cosmos in just a few slides. Similarly, now that dust could form inside a giant interstellar cloud. And so we've got background stars trying to radiate different types of photons at us. And as it penetrates the gas cloud, only certain wavelengths of light are really capable of getting through. So the clouds and dust, what they do is basically filter the light that can get to us. So when the dust is, right, as this dust absorbs photons, it gets hotter, and now it's a hotter object, it will glow, and it has to be a thermal photon. Go back to section 5 for a brief recap of that. And so it absorbs this energy, and then it will glow in a bit more of an infrared spectrum. Thermal photons is the language that we like to use. And the same thing across the whole spectrum of the crowd. So what happens is that as we look across the cosmos, if there's gas and dust in our way, the stars are going to become a little bit fainter and a little bit redder. This is redder in the sense of shifting the wavelengths of light, but not the same thing as a Doppler shift. I have to distinguish between Doppler shifting and the reddening due to material blocking the light. So let's actually look at some pretty pictures, some actual examples of this in action. All right, here is a visible picture of the Milky Way, and we see the band of the Milky Way. There's definitely a concentration of light near the center of the Milky Way. And as you get further away, not as much stuff. We start to see more and more background stars, right? And this is our world, this is our view of the Milky Way and the visible spectrum, what our eyes can see. Let's shift the wavelengths. if we change what wavelength of light we see, we're going to change what layers of the cosmos we get to see. So here's the same picture of the Milky Way galaxy, but this is images pulled from what's called the Wide Field Infrared Survey Explorer, right? What it's doing is trying to capture wavelengths of light that are in the infrared spectrum, 3.4, 12 to 22 micrometers. So this is the below red. Our eyes can't see this, but we can build detectors to get these wavelengths of light. And we're seeing a lot more bands of material. We're seeing a lot more stuff out in the cosmos. If I go to even longer wavelengths, keep going, in our Milky Way galaxy, yes, we still see that clear defining line that is the Milky Way. But look at how filled the Milky Way is. And this comes back to what I mean about there's gas and dust out there. It's blocking a lot of the light in the visible spectrum. But that infrared, that long, these are wavelengths of almost a meter long. How do we get that picture? So radio telescopes. These are telescopes that are sensitive to wavelengths of light between micrometers to a meter. IRIS and COBE, I believe, are satellites measuring at those long wavelengths of light. And they scan across. Does far infrared mean long wave infrared? Yes, those are the same thing. So basically, as we're going across our electromagnetic spectrum, we're going longer. So the takeaway from this, yes, the Milky Way is just filled with tons of stuff. And when you look at it with the correct wavelength of light, you get to find more things in the cosmos. All right. All right. So we've gone through our gas. Now let's start. Or we've gone through the dust. Now let's start talking about the dust. I keep messing that up. We've gotten through discussing the dust. So now let's move in and talking about the gas. And here's I love these pictures. You're gonna have examples of a star. This is a newborn star. Was formerly a protostar, and it's got this jet, this geyser of gas and dust flowing off of it. So we're going to start making a connection to the temperature of the gases, their density, and their relationship to the star or whatever got them at that temperature. All right. So let's got a couple of related terms to fill in here. So I tried to color code these to distinguish between them, and I'll have some pictures in the next few slides to help fill in the void of what I mean by these different terms. So let's start bigger. All right. We're gonna have our interstellar gas. And that is kind of just a blanket catch-all term. This is the gas and dust between the stars, similar to interstellar medium. When we say medium, we're talking about everything in there, including sometimes radiation. If I focus down into gas, I'm going to focus on the gas between the stars. Then we talk about interstellar clouds. And by interstellar clouds, we're going to say these are quote-unquote high densities. Right, there is a larger concentration of atoms there. Right? Nebulas are going to be good examples of these types of clouds. Right? So you're going to have high density regions of interstellar space. And then the remaining bits, whatever's not inside the interstellar clouds, is what we call the intercloud gas. So interstellar gas, take of all of the space and say, what's all the gas there? Now, interstellar cloud, think of a concentration. There is a pocket of gas here, right? There's a big cloud, and that cloud moves around through the cosmos. So, big picture, interstellar gas, a cloud, that's our interstellar cloud, and then everything in between the clouds, is going to be our intercloud gas. So this is the big catch-all, and then we're narrowing down smaller and smaller concentrations. So let's start comparing some of these properties. If I have, say, a hot intercloud, right? If I have a hot intercloud, we're going to talk about temperatures of upwards of 1,000,000 Kelvin. So this is the stuff between the clouds. It's going to be very hot, very low density. There is not a lot of atoms here, but the ones that are there, they're whipping around very rapidly. So these, you can think of stuff that got ejected off the star or maybe propelled through the cosmos by like a supernova, and they're just flying through the cosmos. All right. We're going to go down in temperature. This table is grouping them in terms of temperature. If we get to what, say, is a warm intercloud gas, so we're not inside nebulas, which is just the warmer material, the density's gone up. There's a bit more of these warmer clouds, and they've cooled off. They're closer to about 8,000 Kelvin. Still running around rapidly. And keep going. You've got the colder gases, the density's going up. Notice the relationship. The faster, or specifically the hotter the particles, the lower the density. That's a key relationship. Right? If you're really hot and flying around, remember, these clouds don't have any sort of gravitational body really to hold them in place. So as they just disperse because of their rapid motion, the faster you move, the quicker you get away from each other. All right, great question. Does the cloud float freely, or is it orbiting something? These clouds are not orbiting anything specifically. They are just out there in the cosmos, and they'll have motions where they're slowly expanding in size or sometimes collapsing down. And the motion of these clouds, you kind of can think of them as like clouds in our atmosphere, how just the random winds push these clouds around. Well, here on Earth, the winds are due to changes in pressure. Out in the cosmos, the stellar winds, well, that's due to, saying, stars ejecting material or supernova pushing things out. And so, yes, these are clouds that are basically free-floating. They're not bounded to anything. What we'll find is that these clouds are thousands of times bigger than any stars, and there'll be houses for stars to start forming inside them. So, let's come down here. About half of all the interstellar gas is trapped in the clouds. And that's what I mean about, like, these clouds are going to be star birthing regions, right? And the clouds themselves, about 2% of space. So remember, big vacuum, big void of emptiness, and then pockets of higher density, right? So half the gas in the cosmos are in these clouds. Those clouds are concentrated into tiny space, so the rest of that big void is that intercloud gas. Think of the hotter, rapidly moving stuff. So some pictures to try and help us with these terminologies, trying to narrow these down. Here's a great example of an interstellar cloud. This is a Cephas b. It's called a molecular cloud. That thing's only a few thousand light years away from Earth, so it's definitely in the Milky Way. This is something you're going to start noticing, is we're going to start distinguishing, are these things that we're seeing inside our Milky Way or outside? And most of the grandiose pictures we see, they're going to be inside our Milky Way. So here's a cloud, and you literally can start seeing regions of, this is not a star behind the cloud, it's a star inside it. So these clouds are these massive enveloping things that are just floating through space. Then we have things like the intercloud gas. So this is, once again, looking at the full range of the Milky Way, and we're just seeing the wide range of gas that's just glowing, right? And in the next few slides, we'll start talking about what's the source of their glow, and specifically what wavelengths of light they tend to glow in, or what temperature they're at. So, go back a bit. Interstellar cloud. These are technically denser regions of space, but this can still be hundreds of light years in size. You can find pockets of even denser regions inside the cloud. Now, get outside those clouds, and there you'll have the intercloud gas, which is just the gas spread throughout the Milky Way. All right. So let's have an example of talking about just the intercloud gas, right? We can still find a wide range of temperatures. Remember, these things can be hundreds of light years across in size. So that means that their temperature can be wildly changed. We could have something like a supernova explosions. Supernova, for our purposes, is just going to be a big massive star collapsing and just blowing up. And I do promise we will talk about that in more detail. But for now, we'll just say big star went kaboom. And when it does, that heats up a lot of the gas in that region, gives them a lot of thermal energy and specifically kinetic energy to just fly through the cosmos. So you can have very hot regions, right? We can also have regions that are star forming. So big giant gas cloud. If you want to continue the analogy we started earlier, clouds floating through our atmosphere and it's forming raindrops to pour down on us. You can think of it as similar. There's the intercloud floating through space, and inside that cloud there will be regions where things are condensing down enough to start forming stars. So, wide range temperatures and wide range of regions of what is producing the dominant glow at these regions of these clouds. We can have ionized gases. And an ionized gas, what we're mostly saying is hydrogen with no electrons. That's going to be the bulk of what we're talking about. Hydrogen with no electrons, so just this charged particle floating around. And these things are going to be upwards of that million of Kelvin. Cool down a little bit, get away from the big explosions, and you're going to find sometimes a lot more neutral gases. And that's where they tend to glow at around 8,000 Kelvin. And the spectrum of light is going to be this H alpha line. I'm going to go over this in more detail. What the heck does this H alpha line mean is? But the emphasis I'll say now is that H alpha tells us how we know that there's a lot of neutral gas in the cosmos. And then keep going, you can find things like molecular gases. This is going to be gases of a bunch of atoms sticking together. They're going to radiate in a bit more of the long radio waves. Remember, like the meter-long wavelengths, right? And what's producing this spectrum of light we see is going to come from what we say spin flips. So I'm going to go through these in a bit more detail. All right, it's just not good enough to have the text there. So, breaking that down, let's have our hot gas. And this is a picture we had at the very beginning of this section. We said, look, we live in a bubble of X-ray gas, right? Upwards to millions of Kelvin floating around. So these are high energy charged particles flying around, and they're naturally giving off X-rays because of how fast they're moving. So we look across in an X-ray spectrum of the Milky Way, and we see tons of X-rays. And you're also going to see some brighter spots, right? Those bright spots are most likely what we'd say recent supernova. Recent is a cosmological timescale, so we're saying thousands or tens of thousands of years recent. But either way, recent in the sense that a star blew up, and when that happens, an insane amount of energy gets violently released. And so we'll find these brighter spots in the Milky Way of X-ray radiation from the big violent explosions. And that produces the hottest gases that we see out there. Now we cool off a little bit, right? Now we're going to start seeing things like pictures like this. We're going to see a lot of red and a lot of glowing spots, right? So the red, that's going to be the stuff that's in terms of about 8,000 Kelvin. And this red literally comes from what we say, this is the H alpha line. So what the heck is the H alpha line? This is an old chemistry term, in essence. Spectroscopy term. So some of you might remember, we've talked about this before, the Balmer series. These 4 lines here, this is chemically identifying hydrogen. You're looking at the atomic properties, and that's what this picture is. Here's your hydrogen atom, 1 proton, 1 electron orbiting around it. And we say, what energy shell is that electron in? And for this line specifically, this wavelength of light, it gets produced when an electron starts at this energy shell, the n equals 3. So remember the bookshelf analogy. You start off, right? If you start off at a high shelf and you drop to a lower shelf, you start high, go low, you spit out a photon. And so by spitting out a photon, this spin here, the H alpha line, corresponds to this reddish glow. So when we see the Milky Way, this is part of how we know most of the universe is hydrogen, is that we see almost entirely hydrogen lines. Now the brighter parts, you'll notice they're a bit more concentrated towards the galactic center, concentrated where there's a lot more stuff flying around. So this is what we call an H2 region, and that's just a older term to say ionized hydrogen without electrons on it. And so the gas here is going to be a little bit hotter as it's flying around potentially more stars that are being crushed down in more stars. All right. Finally, we'll reach the coolest of the gases. All right, we're going to keep cooling down. And you start to see the longer wavelengths. Think back to the last part. Whereas we extended the wavelength of light we see, if we make the wavelength longer, we get to see more and more material. So we cool down. We get into what's called the H1 region. H1, proton with an electron bounded to it. That's all we need to know. It's proton with an electron bounded to it. These are going to be cooler gas molecules, and they're going to be radiating in this wavelength of 21 centimeter line. And this comes from what's called an electron spin flip. Right. The example we like to say is take an object, spin it around. Right. This is a classical analogy. It doesn't work correctly for this. But I can say I have this pin spinning around and say, well, what's the rotation of this one? And then if they sync up, if I ever not drop them, I can say, do they sync up or are they opposite directions? So they're rotating in unison. I do not have the dexterity for this. They can rotate in unison or opposite each other. Right. That's our classical way to think of atomic and electronic spin. So you can say, look, the spin of the nucleus versus spin of the electron, and they'll flip. They could be in unison or they could flip around. And that result of this electron, of those electrons spinning around, that spits out a photon. It's a very low energy photon, which is why it has such a long wavelength, 21 centimeters. You're talking about a wavelength of, honestly, not much, a little bit shorter than the length of my paper here. A wavelength that goes probably about right. About that length is what the wavelength of the light coming off from this spin flip. So it is very much a cooler spectrum. I'm going to not respond to the silly jokes, but I do appreciate them. So, the electrons are cooler, and it's the spin flips that are kinder, right? I'm looking out in the cosmos, and say there is a star, and then a cloud of dust between us. What happens to the light of that star? We've talked about this before. Do you guys remember? All right. So first answer I see was a redder from the Doppler shift. And gotta be specific here. It is not redder from a Doppler shift. Doppler shift is going to be a different, but close. All right. So what happens is, what that gas cloud does is it tends to block a lot of the visible light, especially a lot of the ultraviolet waves, and it tends to glow in the infrared. So yes, the light tends to be redder, but it's not a Doppler shift. Doppler shift is due to the motion of the star towards or away from us. This is going to be a shifting of the colors because something's blocking it and then getting heated up. So let's have a picture of this, right? We're going to have what we call these molecular clouds. We'll have these molecular clouds. So you're going to have stars across the spectrum, and then we're going to see just these dark voids. And these dark voids are not going to be black holes. That's a common misconception that this is a black hole. No. This is just a cloud of dust between our view of the stars behind the clouds. So it's darker because it's blocking a lot of the visible lights. All right, so a question that comes in. Is it because the red color has less frequency and a longer wavelength? Correct. The longer the wavelength, the lower the frequency, the higher the probability of it being able to pass through the material, in essence. And that's why we tend to see a redder color. So, when we see dark bands like this, we'll have another picture and we'll fill in the red colors that are missing. All right. So, this is a big molecular cloud. A lot of hydrogen. And another question. Do the clouds not reflect light? They reflect some amount. And if they reflect that light, then it's very unlikely to be reflected, bounced towards our eyes. Remember, we're talking about grains that, like, even this is orders of magnitude too big. These grains are at max 300 nanometers, so they're going to be tiny. All right. So let's look at this picture with infrared stick glued on top of that. And there you can start to see the stars hidden behind. So often question, how can we tell these apart from black holes? Well, it's a little tricky, but one of the biggest answers is that these black voids are significantly easier to spot than black holes. It's because that this thing is blocking a huge range of light. So the cloud itself is very close to us relatively to the stars. So this cloud is very close, which means it has a huge angular size. Think back to when we talked about the angular size of the moon versus the sun. The closer something is, the bigger angularly it is. So these glass clouds have a huge angular size, which makes them much easier to spot, Whereas the black holes in the universe, they're going to be a lot further away from us. And so we are less likely to be able to see them. And on top of that, these molecular clouds are going to be gigantic. Black hole will be a couple of times bigger than our sun in terms of its horizon. This cloud could be hundreds to thousands of light years in diameter. And so the cloud itself is just significantly bigger than a black hole. So what we've done here is stitched on looking at this molecular cloud with an infrared spectrum. And we can just see all the stars that are basically behind it. And doing some tricks with some radio waves, we can figure out some properties of these clouds. And they're very cold. They're on average around just 10 Kelvin. But there's still a lot of mass in there. This one in particular is about 107 solar masses. And size here to here in this picture is 120 light years. An event horizon is going to be smaller than a light year. And that comes back to the previous question of why are these easier to spot than black holes? They're significantly bigger. All right. Get some water. So how come these clouds didn't absorb the light and glow? They are glowing. So this picture came from. Let me start with the last one. So they are glowing. This picture, this was specifically research trying to figure out how to view what was behind it. And their work, they produce this wonderful image to stitch them together. So we could shift the wavelength of light that we want to look at and see the specific glow of the dark cloud itself, because it's only dark in the visible spectrum. So the cloud itself is glowing, and if we pick the correct wavelengths of light to look at it, we'll see the constituents of the gas itself. And that's how we know things like it's glowing in these radio waves and its temperature. All right. Is this about star birth too? Rivers, this is exactly what we're tying into, the relationship between this stuff and the birth of stars. So let's wrap this section off of all this big gas and dust spread throughout the cosmos, and we'll tie them back into the stars and how they're starting to be birthed. And Orion Nebula, great example of this gas and dust floating around, and where you're going to find star forming regions. So on the right, we could have like our molecular cloud. And one way to think of a molecular cloud is that it's a star birthing factory, right? A lot of gas around here could start pulling together from just gravitational forces, and protostars can start to form in there. So as we look across the cosmos, where we see the density of stars or how they're dispersed actually gives us an idea of the age of the stars, right? The younger a star is, the more likely they're going to be clustered together because they formed inside the molecular cloud. So they're going to be close together when they went from protostar to star. Now, as the stars age, they still have some amount of motion in some random direction. So as the stars get older, the cluster of stars start to spread out. They start to disperse. So our young stars tend to be clustered together, whereas the older stars, because of just how long this is just bullet points of information. The exact sequence of going from molecular cloud to old stars is actually very complex and not fully understood. We don't have every piece of the picture of forming here to spread out. So think of these bullet points as just observations that we've made so far. Right. So, last comment to make on this slide is that as the stars compress and spit out material, the massive stars, they tend to create a lot of ultraviolet radiation and high-speed gas. So the more massive a star is, the more likely it helps distribute the material in the molecular cloud, because it's releasing so much energy that basically is punching holes in the cloud. So now coming into a sequence of events. Here is an example of sequence of events of going from big cloud down to that star. And this is a bit of a recap from what we saw back in section 7. Right? You have dense cores that form molecular clouds. So here's my molecular cloud. In this diagram, we're talking 5,000 astronomical units in size. Right? So this big, gigantic space. And if I was to zoom in on just one of these cores, so this material is just slightly denser regions inside the cloud. Zoom in on one of those denser regions, and that's where you're going to get your protostar. Remember, gravitational collapses, the protostar starts rotating faster and faster as gravity collapses in that pocket region. Right? So the protostar is all that hydrogen gas collapsing down, falling together, and eventually it's going to start producing a stellar wind. Basically, gravity's trying to squeeze things in, the rotation. What happens around the poles is that the star is literally ejecting material out. It's throwing material out into the cosmos. And we're going to see examples of this, these jet streams that these protostars form. And then eventually, that protostar will have condensed enough to collapse down into a single star. And it'll disperse all material around it. All right. So here's an actual picture of a protostar and its corresponding jet stream. Notice this is over the space of a couple of years of the pole of this protostar constantly ejecting material out. Protostar formation will be upwards of thousands of years of it slowly collapsing down and ejecting gas in the cosmos. And here's another source of, say, hot gases in the intercloud space. This is material that didn't get absorbed by the star. It's not going to be part of its mass, but it got heated up and just flung out in the cosmos. So, like I said in the last section, we're going to start seeing these HR diagrams more and more because they're going to help us map the evolutionary paths. So as a reminder, right, this red line is what we say is a main sequence stars. And our sun's somewhere around here in the G range of the spectrum on that main sequence. But the protostars, we still can plot them on the HR diagram. Remember, here's the luminosity versus the surface temperature. So you could have a star kind of like our sun, about 1 solar mass, and it'll be, at this point, still a protostar. And there's some interesting physics happening in its outer layers. Notice, the protostar, as it's getting older, is shrinking down. All right. What we're going to look at, I'm going to focus on this line here, right? The numbers on each line, these numbers here, they represent number of years. So if I start with a very massive star, that very massive star takes only about 10,000 years to go from denser region of the cloud to forming a star. Whereas the low mass stars, one that's like the 10th of our sun, they can take upwards to 1 million to 100 million years to finally collapse to a star. So the high mass stars will quickly, high mass protostars will quickly turn into a star. Low mass ones take a long time. But notice the track that they follow, where they take this long, this almost vertical track down. We call that the Hayashi track. So, points. The protostars, they are going to be more luminous than a star of similar size. The stars are going to be more luminous when they're way up here. The protostars are more luminous. And as that protostar shrinks down in size, right, it's going to start getting cooler. Its luminosity is going to decrease until eventually it hits the main sequence. It turns on fusion and starts to glow bright as a star. Right. So that's going to be the end of our discussion on the interstellar material out there. Just a quick reminder. We said space is a very low density, but gigantic. There is billions and billions and billions of matter out there. And it's just dispersed in this huge, gigantic space. We've talked about how the gas and dust literally changes our perspective of the universe, sometimes blocking things, other times we can see through it using the right wavelengths. And the interstellar gas can have a wide range of temperatures, anywhere to being only 10 Kelvin. This is only 10 degrees Celsius above zero, upwards to a million or so Kelvin because they're so energetic, rapidly flying around. So this gas has a wide range of kinetic energies and corresponding wavelengths of light it radiates in. And that final point is that you take a collapsing protostar to make a star, and as it collapses, it releases tons and tons of energy. So we'll call that into section 15, and I'll see you all next time. All right. So I'm seeing questions about, is the stream broken? Let's just try there. All right, so it looks like it's still going fine. So yes. All right. So to the website. So if the stream broke at different points, I do have just a recording local to my machine, so I will be able to just upload those hard recordings if at any point the stream broke down. All right. So I saw someone said they had a question, so it's presumably they're still typing their question. So I'll wait here patiently. All right. I see. Yep. I see people are leaving the stream. A few are still here. I see the cruel world is giving me 2 thumbs up and 1 thumbs down. Okay, so it looks like there's a bit of a delay in chat. That's fine. All right, so why do galaxies form in the shape of disk but planets form in spheres. All right. So what we're going to find is, what's the easiest way for me to do this? Let me pull up some pictures of these. So what we're going to find is that not all galaxies form into disk. Some are going to form into these weird elliptical, irregular shapes. So let's go to the website. But like the quick answer is that planets, stars, they form spheres because we're tiny enough. Gravity can be the dominant force on us, and so gravity just collapses things down into a spherical pattern. When you get to the size of galaxies, you're going to have other factors of what's basically holding them. Yes, gravity is that primary force, but because of the sheer size and distribution of material, you can get different patterns that form. And we'll have a whole section dedicated to talking about what creates basically the spiral arms of a galaxy instead of crushing them down to a sphere. So let's see here. I'd be... Is it that one? Let's see here. Did I combine those? So this is my slides on the Milky Way. Now we're starting to get into cosmology. It's cool. Next. So let's say here. All right. Let's see here. If I go to, let's turn off the pen press. There we go. So, emphasis. There can be different shapes of galaxies. Like, spiral is the one we most predominantly think of, partly because we live in a spiral galaxy and they're very pretty pictures. But you can get elliptical, almost spherical in shape, or just debris of stars and dust that are gravitationally bounded to each other but do not have any cohesive shape to them. All right. So the galaxy's 2D flat. A lot of the galaxies fall into that shape. A lot of galaxies fall into this 2D flat shape. Now that's a great question. What defines a galaxy? I'll go with the easiest one. For spiral, you can basically clearly define this region material that is bounded together. It's by gravity, and it's not just the luminous matter. We'll see that this stuff is rotating around in some manner. And it's this local in the size of galactic scales, local collection of stars and dust trapped together. A shortcut, you could talk about the supermassive black hole at the center of the galaxy that's keeping all this gravitationally bounded together. Each one of these has a massive black hole at their core, basically. Even the weird irregular one. Yeah, absolutely. So, like you can't see in this picture because the resolution's just not fine enough. But like this little bright spot here that I'm kind of like highlight, that's honestly just pockets of potentially thousands, if not millions, of stars. Uh, so you'll still have stars of planets orbiting around them. We have to start thinking in completely different distance scales here. You'll have heck, even in the void of space here, there's probably a star with planets orbiting around the star in this void. So yes, even in the irregular galaxies, planets still orbit their stars in ellipses. It's the big cosmological scales where things are getting wonky. If I was looking at space, I would have classified the irregular galaxy as wandering dust with planets. Um, a lot of the first astronomers did. A lot of the first astronomers did do that. A big debate often when you are looking out there is trying to figure out what is basically how big is this? How massive is this? And the reason we know this is not just a collection of dust is because of just the sheer size of it. All right. So, River's question, does it have to do with gravity? Yes. Once again, I'll take my shortcut and just say we know that there's going to be a big, massive black hole at the center of all of these galaxies. And that massive black hole has a huge gravitational influence that keeps these things bounded together. Furthermore, looking at pictures of galaxies like this is why we know stuff like dark matter exists. I've hinted at it a couple of times, but not made it like an explicit statement. But basically, you see all the glowing stuff, the glowing matter, we call it luminous matter. When we talk about dark matter, right, you say, well, how much matter is in this galaxy that we can't see? We know it's there because of, one, the stability of the galaxy and the rotation rate of the galaxy. We know these galaxies are several times more massive. All right, I can kind of reset. What should I do? Okay, Rivers, I'm going to advise you to send me a question about that. I'd rather not answer questions like that through a chat or on the stream. That's fine. That's fine. So it's just that I don't want questions of potentially personal information accidentally slipping through the stream. That's all. So shoot me an email and I'll answer that question then. All right. So I think we've kind of wrapped up on the questions. So with that, I'll call it a day here. Hope everyone had a good lecture. I hope everyone's staying safe, staying healthy, and I'll see you all on Thursday.